When we started this course, we entertained a numerical problem involving the square root of a number. In particular, we were looking at the square root of 5. So I proposed an algorithm without much justification that was fairly short, and it very happily converged quickly into the square root. What we were really doing is we were finding the root of a nonlinear equation. In particular, we were finding the root of a quadratic. The quadratic was x squared minus 5. So what we were actually doing is finding the roots of this quadratic. And what we will find in this section is that most nonlinear equations can be solved through root finding mechanisms. In chapter 2, we really had an easier problem. We were looking for solutions to linear systems. We were allowing many equations and many unknowns. And the only thing that really gave us a problem with respect to finding a solution is if we had a system that wasn't a full rank. So if we had a matrix that was singular, then okay, we had a little bit of trouble with that. But at least we had a method to find the rank and determine quickly if that problem existed. The rest of the course was really devoted to what do you do with full rank systems that were always guaranteed to give you a unique solution. When we move to nonlinear equations, we don't have that luxury. We will typically get more than one solution, and the multiple solutions probably have valid interpretation. So we'll have to apply some scientific or engineering knowledge to determine which of those solutions we want. But in addition to that, we're also going to have to be careful with our algorithms that we know which solution we're chasing after and how many other solutions there might be out there. So that's going to be somewhat of a big deal. So with that, we're going to turn to a problem that has no explicit formula for a solution. And the equation of interest is the one we're looking at in front of us. Now you may say that looks like a pretty simple problem. I could scratch out the solution to that very quickly. Go ahead and try it. Take it home after this session is done and see if you could come up with an explicit formula for y. I don't recommend spending a lot of time at it because I think you'll have a lot of trouble doing that. Nevertheless, a solution does exist. Perhaps more than one solution exists. How can we then go after a solution to a problem for which we're going to have trouble finding an explicit formula? Well, one method that comes to mind very quickly would be to graph the left side and the right side separately. So we could look at the left side as a linear function of its own, call it f1, and the right side is a logarithmic function, and we can call it f2. If we graph those both separately and look to see where they intersect, we could even draw up a line from the intersection point down to the y-axis here, and we could find what value of y caused these two functions to be the same. Well, that's the same thing as asking when is y plus 2 equal to the log of y. Now, if we just do that visually a little crudely, I don't know, maybe it's around 1.12 would be the value that produces an intersection and therefore a solution. So what we're going to do with this equation is come up with a method that we could program that would solve any kind of nonlinear equation, well, up to a point. And we will start by subtracting the log of y from both sides of the equation, creating some function on the left that must be equal to 0 for this relationship to be true. So that's what we've just done here. We've taken y plus 2 equals the log of y and said it's the same thing as finding the root of f of y, where f of y is y plus 2 minus the log of y. Let's go ahead and graph that and see what it looks like. Here we have a function now that's very nicely just dropping down through 0. In fact, it's easier to pick off the root visually, and we can see it's a little bigger than 1.12. So we've improved our graphical approach, perhaps, but we still haven't come up with a nice systematic algorithmic approach to find those roots. Let's just switch the problem a bit. We're going to go ahead and try to create a nice systematic solution, but let's do it with a simpler problem, and we'll pick some nice quadratic. Now this quadratic is nice also because it factors so easily. So if my goal is to find out where does f equal 0, I can do it quickly with algebraic methods by just factoring the polynomial and then solving each piece, setting each piece equal to 0. And we end up with the result x must be 2/3, or it's going to have to be 1/2, one or the other. Both roots are possible. And so which one do I use? Well, again, that is going to end up being a engineering decision or a scientific decision on whether one or the other or both roots actually make sense. But from a mathematical point of view, we want to have a way to solve for those roots numerically, even if the equation isn't as pretty as the one we're looking at here. In this case, it's nice to have an analytic check against a numerical solution. So that's as far as we'll get in this section. Now we're going to go through a series of potential solutions to the problem. We'll start with the easiest one called the bisection method, where we take very conservative guesses on both sides of a solution and try to cut the interval in half and half again and half again to converge onto the result. And then we'll move on with some even better methods than that one. And so with that introduction, we will close this section and see you next time.